Okay, in this presentation we're going to look at solving ODEs using Laplace transform, second order ordinary differential equations. Okay, so here we have an ordinary differential equation, second order, d squared y over dt squared plus d2 dy over dt plus y equals 1 plus 2t. Now we have these initial values here, boundary conditions. The derivative of y0 is equal to 0 and y0 is equal to 0. Okay, essentially we're mixing up our notation here. So what I'm going to do is actually just re-express the whole thing in terms of the notation that is consistent in the tables, the Laplace transform tables that I use. So what we're going to do here is actually use the Laplace transform tables to, my table is rocking there a bit, to actually sort of, particularly the left-hand side of the equation there, to actually just come up with the equivalent Laplace transform of each. Now again, the boundary conditions are important. Okay, so the Laplace transform of the second derivative of y of t is, I'll just move that up there a second, just let that settle. There we go. Is okay, so that is the second derivative there of y is s squared times capital Y of s, that's the Laplace transform of y itself, minus s times the derivative of y0, okay, and again capital S here, lowercase y here, s domain here, t domain here, and so on, minus y0, okay. Now, the boundary conditions are such that these terms cancel out because they're 0. Okay, watch out for that because that might not always necessarily be the case. Okay, quite often, just one of the more sort of easier examples, they straight away sort of cancel out to 0. Not always the case. It actually happens to be the case here. So essentially, it just resolves to s squared times y of s. Okay, so that's the first term. The second term is the derivative. The Laplace transform of the derivative of y, okay, equals s times y of s minus y0. And again, this just this is 0, so this just resolves itself to s times y of s, okay. Just a remark there that the coefficient is 2, so we're actually going to put 2sys into the equation, okay. That's just actually what's in the tables, but the coefficient, the multiple, it's a multiple of 2 there, okay. And finally, the Laplace transform of y is y of s. Okay, so what I'm going to do is actually sort of piece them all together. Okay, let's just go to the next page here, and so this sort of piece it all together, and I'm going to just sort of take out the y of s terms, so it's all separate. So I just have this little quadratic expression. The left-hand side, the Laplace transform of the left-hand side is s squared plus 2s plus 1 y of s, and you might notice that that is s plus 1 to be squared. Okay, so now what we do is get the Laplace transform of the right hand side. So this should be fairly straightforward. A Laplace transform of 1 plus t is 1 over s plus 1 over s squared. Grand. Okay, so you can just actually sort of re-express that as s plus 1 over s squared. S plus 1 is back. Remember that. Okay, so what we have here is, this is the Laplace transform of the left hand side, this is the Laplace transform of the right hand side. What we do is we actually can factorize that, and so that will cancel out there. Okay, so we have, I'll actually just won't do it in too many jumps. S plus 1 over s plus 1 squared times s squared, that should be squared there, sorry, pardon me. Okay, so there we go. So that anyway, it just resolves itself down. So we have 1 over s plus 1 times s squared. Okay, I'm just going to sort of pause a second because I just dropped my page on the ground. So sorry, I just actually sort of pick up there. So capital Y of s, which we found to be 1 over s plus 1 over s squared. What we're going to do is sort of simplify that. And what we're going to use here is partial fraction expansion. Now, so I'm not going to get too much into what partial fraction expansion is about, but essentially we have this term here, and we write a over s plus 1 plus, this is a polynomial of degree 2, so we have a polynomial of degree 1 above the line there, okay, which is bs plus c, okay. So what we have to do is sort of simplify that and find out what a, b, and c are, and then just get the inverse Laplace transform. So it's a bit of a, oh, here we are. It's a good bit of a number crunch there. So we cross multiply a times s squared, okay, plus bs plus c times s plus 1. So we have bs squared plus bs plus cs plus c, okay. And, oh, that's over s plus 1 over s squared, okay. So essentially what we just got to do here is just round up all of the terms. A plus 1 s squared, sorry, a plus b s squared plus b plus c times s plus c. Okay, it's a bit of a tongue twister there, but if you just sort of follow what's going on, it should work. Okay, so this is equal to y. This is equal to this expression here. Okay, is equal to. I'll just bring it back into shot. This expression here. Okay, 1 over s plus 1 times s squared. Okay. So what I'm going to do actually is rephrase that as 0s squared plus 0s plus 1. Okay? And that means, sorry, just went a little bit too far there. That means that this a plus b is equal to 0, b plus c is equal to 0, and c is equal to 1. So c is equal to 1, b plus c is equal to 0. That means that b has to be equal to minus 1. A plus b is equal to 0, so a has to equal to 1. Okay? So what we got here, y of s equals 1 over s plus 1 minus 1 over s, which is the b. Essentially what I've done here is just broken up bs plus c into two parts, and the s cancelled out. The s and the s squared cancelled out to 1 over s. And then 1 over s squared. Okay? So that's the bs over s component, or bs over s squared component there. And so what we do is use the Laplace transform tables to get the inverse Laplace transform of each term there. It should be straightforward enough if you've come this far to go to find the inverse Laplace transform of 1 over s plus 1 is e to the minus t. Minus 1 over s is simply minus 1, and plus 1 over s squared is t. So just bundle it up there. I think just no particular reason going from this to this. I just like the t on the left hand side. T greater than or equal to 0. Okay, that's it.